Technology. And this year, the award goes to Dr. Irena Francis-Creed, who I believe is here in person. And just before she starts her presentation, I'd like to say she works on advancing understanding of how climate change alters the movement and transformation of water, carbon, nutrient through couple atmospherical terrestrial aquatic system from headwater to wetlands, stream, and lakes. So covering a lot of ecosystem. This is really awesome research. I invite you to look a little bit more at what she does, and she's going to talk more about it right now. And without further ado, I invite her to come and give her presentation and also give you this. Thank you.
Well, thank you very much for that introduction, and it is truly an honor to receive the Frank Rigler Award, in part because his work has shaped so much of how we think about limnology. Frank Rigler's work emphasized system thinking, simple organizing principles, and linking process to prediction. He believed that careful measurements should lead to transferable and scalable understanding, relationships that allow us to predict how lakes behave. That philosophy transformed limnology into a more management or use-inspired, as Joey just said, relevant science. If there's one thing that he is known for, or one theme that most strongly characterizes his work, it is phosphorus. Around 1975, the Dillon-Rigler phosphorus-chlorophyll relationship became one of the defining examples of that approach. And 50 years later, we are still building from that conceptual foundation. Today, I want to revisit that relationship, not to replace it, but to ask how climate change, watershed rewiring, and microbial interactions are modifying its expression across lakes. So 50 years later, the key question becomes, does the classic TP-chlorophyll relationship still hold? And more importantly, what controls the delivery of phosphorus to lakes? Do lakes respond differently to the same phosphorus concentration? And when does eutrophication shift towards cyanobacteria dominance and toxin production? So the first top part of this talk focuses on the hidden hydrologic wiring of watersheds. The key idea is that the phosphorus-chlorophyll relationship begins upstream. Many of the most important watershed controls on nutrient export are effectively invisible. Early in my career, I showed that cryptic wetlands and streams incognito are hydrologic features that are often hidden or poorly mapped because of their small size. Yet, they disproportionately regulate phosphorus, but not only phosphorus, carbon, nitrogen, and iron export as well. These systems can behave either as nutrient sinks or sources, depending on their hydrologic state. So watersheds that appear simple often conceal complex hydrologic networks that regulate downstream nutrient export far beyond their size. Oh, there we go. Cryptic wetlands and streams incognito are not passive landscape elements. They are active biogeochemical reactors linking terrestrial, atmospheric, and aquatic systems. They partition nutrients between atmospheric exchange and control greenhouse gases, as well as aquatic export. Omitting cryptic wetlands and streams incognito leads to underestimation of watershed-scale carbon and nutrient fluxes. Further, hydrologic connectivity determines whether cryptic wetlands and streams incognito retain nutrients, transform them, or rapidly transmit them to downstream waters. Wet periods connect the hydrologic system and mobilize stored nutrients. Dry periods disconnect the system, increasing water residence time, intensifying evaporation, and concentrating nutrients and salts in downstream waters. So climatic variability reorganizes not only hydrology, but also nutrient sources and sinks, as well as lake biogeochemistry. Now, these concepts, in part in my gratitude of being in Winnipeg, were applied to the Lake Winnipeg watershed. And I asked it what may be a deceptively simple question. What controls phosphorus export to Lake Winnipeg? Using 37 years of observations across nearly 1 million square kilometers of the Lake Winnipeg watershed, combined with statistical learning models, we found that most wetlands occur in the headwaters, and most are disconnected from streams most of the time. Those disconnected wetlands act as gatekeepers, storing water, retaining nutrients, and suppressing downstream export. But during wet periods, the system reorganizes. Wetlands reconnect through fill and spill processes, activating hidden flow paths, and rapidly move stored nutrients downstream. And the response is nonlinear. Once watershed connectivity exceeds about 50%, nutrient export increases coincide with major Lake Winnipeg blooms. That threshold behavior is critical. The watershed can abruptly switch from nutrient retention to nutrient release. So if the first question was, what controls phosphorus export? Then the next question is, how does wetland drainage affect that transport? We found that wetland drainage increases chlorophyll in lakes within the entire Lake Winnipeg watershed across all of the stream orders. But that wetlands in the higher order streams serve as the watershed's last defenders. Although they comprise less than 20% of the wetland area, their drainage status disproportionately controls chlorophyll in the network of feeder lakes that sustain Lake Winnipeg. Thus, both upstream gatekeepers and downstream last defenders are essential for protection because they determine whether watersheds suppress eutrophication or amplify it. So the key message from part one is this: the phosphorus-chlorophyll relationship observed in lakes is an emergent property of watershed hydrologic connectivity. Cryptic wetlands and streams incognito determine when phosphorus, but also carbon, nitrogen, and micronutrients that are needed for downstream productivity are retained, transformed, concentrated, or exported. So to understand lake eutrophication, we must first understand watershed organization. Part two shifts from nutrient export to nutrient interactions within lakes. Once nutrients reach lakes or are transformed internally within lakes, they interact to regulate phytoplankton response. So the question becomes not simply how much phosphorus reaches a lake, but rather how do the interactions among nutrients reorganize the biological response across lakes? To explore this more fully, we sampled more than 100 lakes during the period of peak phytoplankton across the Lake Winnipeg watershed. And we found that these lakes ranged by a remarkable salinity gradient from freshwater to hypersaline lakes. Now, what do we mean by salinity? Salinity reflects the accumulation of dissolved ions in water. Specific conductivity provides a useful proxy for this gradient. And here I provide salinity classes, which, just to give honor to the late Professor Hammer, who Steve just told me passed away this past year at the age of 100. A lot of this work is based on that professor's work. And so he came up with these salinity classes, and I offer the salinity concentrations as well as their specific conductivity equivalents. What's interesting is that as lakes become more hydrologically disconnected, evaporation concentrates the salts, but it also increases phosphorus, nitrogen, and dissolved organic matter. So in these lakes, we found that the classic phosphorus-chlorophyll relationship still exists, as you can see in this data. Total phosphorus remains a strong predictor of total algal biomass. However, when we look specifically at phycocyanin, our proxy for cyanobacteria, the relationship becomes nonlinear. Cyanobacteria do not simply increase linearly with phosphorus. So let's go back to what cyanobacteria need. This reminds us that cyanobacteria are not responding to phosphorus alone. Nitrogen availability strongly influences cyanobacteria composition, competitiveness, and toxicity. So eutrophication is increasingly a problem of nutrient interactions rather than single nutrients. Scientists have suggested that there are important phosphorus and nitrogen thresholds for cyanobacterial dominance. And in this plot, you can see that when phosphorus is high, nitrogen-fixing cyanobacteria can dominate. When nitrogen is high, nitrogen-rich toxin-producing cyanobacteria can dominate. So below these thresholds, the idea is that eukaryote algae dominate. This suggests that cyanobacteria may shift abruptly once systems cross critical nutrient boundaries. But this is not what we found. Here we show where our study lakes fall across the phosphorus and nitrogen gradients. And what becomes immediately striking is that all lakes across the salinity gradient have lakes that are neither phosphorus or nitrogen limited. In fact, that is the dominant nutrient status across the salinity gradients. And I think this is a very important result. It suggests that simple phosphorus and/or nitrogen limitation frameworks may not fully explain why cyanobacteria dominate across these lakes. We need to go deeper. So if we go back to my cell here, you will see that another nutrient that phytoplankton need is iron. And it's also needed for nitrogen uptake, but also for photosynthesis. Under iron-limited conditions, cyanobacteria have an important competitive advantage. They produce something called siderophores, specialized iron-scavenging compounds that allow them to access iron more effectively than eukaryotic algae. So while phosphorus may control overall productivity, iron availability may help determine which organisms dominate in the community. And that competitive advantage may become increasingly important in salinizing lakes, where biological available iron declines. So here I want to show you the distribution of iron across that specific conductivity gradient. But first, to define some terms. Iron prime is the biological available form of iron, the form that phytoplankton can use. And PFE is simply the negative logarithm of iron prime. And previous studies, led by Steve Wilhelm, suggest that it is a critical threshold around PFE of about 20. Below that threshold, iron availability is sufficient to maintain blooms. Above it, cyanobacteria increasingly rely on siderophore production to acquire iron. This provides a potential mechanistic link between salinity, iron stress, and cyanobacterial dominance. Our lakes span a broad range of iron conditions, from non-limiting to extremely limiting. This suggests that cyanobacteria are not responding simply to phosphorus or nitrogen. They are responding to a coupled nutrient metal environment. And as salinity increases, iron limitation intensifies. Cyanobacteria appear to be increasingly relying on siderophores to scavenge biologically available iron, especially in saline waters. This may provide a major competitive advantage under chemically stressful conditions. And using some statistical learning techniques, here we model the nutrient interactions that influence phycocyanin. The strongest predictor of phycocyanin is siderophores. So predicting cyanobacteria requires understanding not only the macronutrients, but also the ecological filters that favor cyanobacteria specifically. You may notice that along the significant predictors, we include manganese and vanadium, and these are both important competitors for iron uptake, so I found it interesting that they too were statistically significant. So this variation of the phosphorus-chlorophyll relationship brings the whole story together. At low resource levels, all primary producers are resource limited, so increases in phosphorus increase both chlorophyll A and phycocyanin. As resource availability increases, conditions may become increasingly favorable for cyanobacteria. Interactions among carbon, nitrogen, phosphorus, iron availability, and microbial processes appear to create an optimal window for cyanobacterial dominance. This is where phycocyanin exceeds chlorophyll A. But at the very high resource levels, the relationship changes again. Other environmental constraints may begin to suppress cyanobacteria relative to total phytoplankton biomass. So the key message is that cyanobacterial response is fundamentally nonlinear. It is not controlled by phosphorus alone, but emerges from interactions among nutrients, dissolved organic matter composition, iron availability, and salinity. And this will take us to the third and final part. Part 3 shifts from cyanobacteria biomass to toxins. As lakes freshen or salinize, cyanobacterial biomass communities and toxicity also reorganize dramatically. In these plots, I show both chlorophyll and phycocyanin. Chlorophyll occurs across the entire salinity gradient with relatively high chlorophyll, even at elevated salinities, suggesting that some eukaryotes can tolerate a wide range of salinity conditions. Phycocyanin behaves differently. Instead of increasing continuously, it peaks strongly at that freshwater saline transition, which is roughly 1,000 microsiemens per centimeter, and then declines at higher salinity. But salinity not only changes cyanobacterial biomass, it also restructures the cyanobacteria community composition. Around 1,000 microsiemens per centimeter, where there was a peak in phycocyanin, we see transition from dominance of Dolichospermum, Aphanizomenon, Planktothrix, towards dominance by Microcystis. And then at around 10,000 microsiemens per centimeter, we see another shift from dominance of Microcystis to a dominance of Nodularia. So what about the cyanobacteria toxins? This figure shows how cyanobacteria toxicity changes across the salinity gradient. What stands out, first of all, I have to just say what stands out to me is that if you see in the red, the WHO provisional guideline for microcystin LR drinking water is 1 microgram per liter. We're talking about levels that go up to 2,000 in these prairie lakes. And what also stands out is that the toxin abundance and diversity is not uniform. At lower salinities, toxin diversity and abundance remain relatively low. At around 1,000 microsiemens per centimeter, where there was that peak in cyanobacteria biomass and a shift in community composition, we see what I call in this graph a minor peak, but still a substantial one in terms of ambient waters, a peak toxin concentration of about 100 micrograms per liter. But also around 10,000, we have a further shift in community composition, and there's a major peak in toxin abundance and diversity, including multiple microcystin congeners and nodularins. And that goes up to about 800 was the statistically significant level, but you could see some outliers approaching 2,000. So salinization may fundamentally reorganize both the ecology and toxicity of cyanobacteria blooms. And when we look here at the model of nutrient interactions that influence the cyanotoxins, the strongest predictors of toxins, once again, is siderophores, but also the molar nitrogen to phosphorus ratio, reinforcing the idea that nutrient stoichiometry, not simply iron scavenging systems, helps determine when toxic blooms occur. So let me finish by returning to Frank Rigler's central idea that limnology should identify organizing principles that allow us to predict ecosystem behavior. The phosphorus chlorophyll relationship remains one of the most important organizing principles in limnology. But what I hope I've shown today is that the relationship is no longer fixed. Climate change is rewiring watersheds. Hydrologic connectivity is shifting. Freshening and salinization of waters is intensifying, and watersheds are reorganizing how nutrients move through landscapes and how lakes respond to that biologically. So the same phosphorus concentration can now produce fundamentally different ecological outcomes, and that means that the next generation of limnology must move beyond the single nutrient thinking towards integrated climate, watershed, lake frameworks. In many ways, I think this still reflects Rigler's original vision, not abandoning simple organizing principles, but refining them as ecosystems become more complex under climate change. And finally, I just want to acknowledge the many outstanding people who have contributed to the work that I've presented. Everything I've presented reflects years of interdisciplinary collaboration among many fields, and I'm deeply grateful to the students, trainees, collaborators whose ideas, fieldwork, analysis, and creativity helped shape this program. And finally, thank you again for this tremendous honor and for the opportunity to give this Frank Rigler talk. But before I finish, I'm really excited that colleague Steve Cook and I are the inaugural and chief of the journal Freshwater Policy and Practice. And I really truly believe Frank Rigler would have been one of the first people to submit to this journal, given his strong desire for what Joey called use-inspired research, what Rigler would have called management-oriented research. And so just to show you the difference of the types of articles that we are welcoming, they include not only research articles, but also policy and practice forums, perspectives, and reviews. It's going to look different. It's going to feel different.